Remote Edge Weather Station. The Remote Edge Weather Station is the CS426 senior project in the spring of 2022 at the University of Nevada, Reno for the College of Engineering's Computer Science and Engineering Department. Team 29 for the Remote Edge Weather Station includes Brendan Aguiar, Nicholas Ang, Daniel Beeston, Dalton Tracy, and Kenji Wan. Instructors for this project include Dr. David Filesheifer, Devin Lee, and Vin Lee. External advisors to the Remote Edge Weather Station project include Dr. Keith Lancaster and Dr. Patrick Arnott. The Remote Edge Weather Station is a complete and fully capable weather monitoring system. The Remote Edge Weather Station, or REWS, is comprised of three large components that make up the REWS system. These components include the REWS device, the REWS web server, and the REWS data visualizer. The purpose of REWS is comprised of three main goals that serve as the pillars to the development of the REWS project. The first goal is to allow users of any experience level to set up and configure a fully capable weather monitoring device without the needless hassle of the hardware and software. The second goal is to allow users to stay informed and understand the weather around them in a simple and intuitive way. The third goal is for the project team to gain experience with the development of embedded systems devices, Internet of Things devices, and developing user applications.
Hi, I'm Dalton Tracy.
And I'm Brendan Aguiar.
And today we're going to be introducing the Remote Edge Weather Station device, also known as the REWS device.
The REWS device is a weather station. It will send all of your weather data through a server into your desktop application.
What kind of weather metrics does the REWS device measure?
I'm glad you asked, Dalton. The REWS weather device measures 7 different metrics. The most immediate ones that we can see here is wind speed and wind direction.
Well, what about some others that others may want to look at?
Well, that's hidden underneath the box. But what do you want to see with the weather? Let's think. Temperature, we got that. Humidity, we got that too. You know, it is a little humid in here.
Ooh.
I bet this weather station could tell you how humid it is right now if you had it hooked up. Well, let's see. What else do we have, Dalton?
We also have air pressure, just to see how hard this air hurts your face. And we also include air quality, just to make sure that nothing's outside and getting in your lungs.
We get too many fires here in the West Coast, so we got to make sure we're keeping track of that. Now let's maybe turn this weather device on so they can see a little bit about how to start it up.
Well, Brendan, let's just see how easy it is to set up and configure a REWS device.
Let's see here.
Let me go ahead and plug it in here.
Dalton's plugging it in. And as Dalton plugs in the device, you'll start to see it power up. And these two LEDs in the front, the red and green one, will blink 4 times.
Takes a little second to get up on the boot, but don't worry, this REWS device is fully capable of measuring your weather metrics.
Powers on immediately, and as soon as it's going, which we see now it's sending to the desktop application.
So now that the box is now blinked 4 times, it's now going to be sending weather data immediately to the REWS web server for your data visualization. Once it blinks, we know that the weather data has been sent.
And it is about there, isn't it now, Dalton?
Almost as good fun as snail racing.
Oh, yes it is. Every 10 seconds, I believe, a snail wins a race.
Come on, REWS, you can do it.
You can do it, buddy. What's taking this thing so long, man? Temporary setback, whatever technical issues are arising in the REWS weather station.
We need the, oh, there it goes.
There it goes. It just takes a minute, folks. Wasn't that exciting?
And there you have it. The REWS device is now perfectly measuring the weather metrics around us and sending it to the REWS web server.
All these weather sensors are connected to an Arduino, and this Arduino sends serially data to the Raspberry Pi. This Raspberry Pi is kind of like a mini computer, and this computer is able to connect to the internet and send our data to the desktop application now.
So now that you know just how functional the REWS weather device is and just how easy it is to set up and configure, Stay tuned.
Get your own too.
Hello, this is Brendan again, and I will go over the sensor communication of the REWS device. Okay. So first, we have the data inputs and outputs. Temperature and humidity sensor use data inputs with timing, but for the sake of this project, we're using a library that handles that. The anemometer and the wind vane also do data inputs. As far as the wind vane goes, there are different resistance levels, and we do an analog read to determine which direction we are looking at. With the anemometer, there is a button that calculates every second how many times the anemometer rotates, and we can do a read and determine the speed from that. Next up, we have the I2C circuits, the integrated circuits. That's going to be the pressure sensor as well as the PM 2.5 sensor, which is the air quality sensor. You see how the air pressure sensor has an SDA and an SCL line. This line is shared between the air pressure sensor and the PM 2.5 sensor, and each have different addresses, so we're able to communicate with one or the other and know which is which. Finally, we have the serial communication, or the UART communication. The GPS has a transmit of the data from the satellite to the Arduino's receiver. And similarly, after all that data is put together into a structure, we send it serially through transmit to the receiving end of the Arduino. And that is all for the sensor communication. This was Brendan Aguirre. Thank you.
Hi, I'm Daniel Beeston, and I'll be talking about the REWS web server and database. The REWS web server serves as a way station for collected weather data on its path from the weather station to the visualizer application. At a high level, the server accepts data sent by the weather station and stores it in a database, where it then can be retrieved later by the visualizer application. Both of these communications are handled using HTTP requests. The server is also responsible for some other minor data processing, such as determining the closest city to the weather station, which is calculated using the station's current latitude and longitude. Unlike the Arduino, the weather station's Raspberry Pi is capable of connecting to the internet, so it's responsible for communicating with the web server. On the Raspberry Pi, the outbound weather data is formatted as a JSON object, which is a common format used for data exchange on the internet. This formatted data is then attached to a HTTP post request and sent to the web server. When the web server receives the data from the weather station, it first determines whether the received data is valid, alerting the weather station if it isn't. Next, the server then contacts the database through a SQL query, which then stores the data for later use. Next, the visualizer application can then request specific data through a HTTP GET request, such as sensor data on a certain date or the station's current location. The server will then retrieve the data from the database, format it, and then send the requested information back to the application where it's displayed. Now for a technical overview of the system. The web server was developed using the Flask web framework, which contacts a Postgres database server. Both the web server and database are hosted on the Heroku cloud hosting service. Flask is a lightweight Python-based web framework. This framework was mainly chosen due to its small learning curve, as our group as a whole has little web development experience. As stated before, our web server and database are hosted on the Heroku cloud hosting service, meaning that both are accessible from anywhere at any time as long as there's an internet connection. This service allows for more convenient setup of the system, as end users are not required to host the system themselves. Heroku also greatly increases the reliability of the system by automatically restarting the server if any major errors occur. Lastly, Postgres is our chosen database management system. Postgres was mainly chosen for the database since it's the only database server supported by Heroku. Being cloud hosted, the maximum data capacity of the database is currently limited to 10,000 rows, but can be extended if necessary.
Hi, I'm Nicholas Ng.
And I'm Kenji Wan, and we will be going over the desktop application. So our team wanted to build an application. So under guidance from Dr. Lancaster, we eventually decided on Qt to build our application. Qt is a graphical user interface framework for many platforms. On the right, you can see our view of Qt when building the app.
So some of the features that the desktop application has is that it could display the latest recorded data, visualize the data into line graphs, allow users to select a range of dates to display. It also features a dynamic color background based on the latest weather data. You are also able to download the latest day's data and delete all data right from the desktop application.
This is the evolution of our user interface. With advice from Vin, we were able to get our user interface looking significantly better. Initially, we didn't have dynamic backgrounds. Some features weren't implemented and boxes were laid out in no specific order. And then in the second image, you can see we cleaned some things up, added more features. We got the dynamic background colors working. And then finally, we gave everything a polish, and now you have our final desktop application's user interface. And now we'll be going to a live demo to show off our desktop application. So this is the home page for our desktop application. It features information including temperature, humidity, wind speed, pressure, and air quality. It gathers all our sensors information all into one easy page where the user is able to just read any of the information at a glance. They don't have to go to any other tabs to read anything. The desktop background is based off the temperature, as that's usually the most important information for a user to have. And then I'll go to the humidity tab to show what a sensor tab looks like. So this is the humidity tab. We have a graph on the left, and on the right we have information about the humidity, which includes a 24 average, 24-hour high, and 24-hour low. We also have a date selector for the graphing range to show. And then I'll go to the settings tab to show you the settings. So we have some simple conversions here and also GPS data. And then I'll pass it over to Nick to go over the features of the desktop application.
So the main feature of the desktop application is its real-time weather display. So it always shows the latest data based on the last updated time. So this is the current temperature from Thursday, April 21st at 9:52 p.m. It also always shows the 24-hour average, the 24-hour highs, 24-hour lows, and then in the wind speed and wind direction, it also shows the current wind direction. And then in pressure, it's a similar panel, and air quality is also a similar panel. And in the settings tab, you can convert the air pressure, wind speed, and temperature to a different unit. So clicking Fahrenheit on temperature converts it to Fahrenheit on both the graph and the panel display. From here, you could select a graphing date range. So you could select 4/20/2022. And then or 21, 2022. And then it will display the graph from yesterday and today. And then in the settings tab, you could download all data. So you can download your data as a text file. And then we'll look at that later. And then you can also delete all your data. So now in the graph, it's blank and is all constantly updating with new data every 5 seconds. And now to look at the data that we downloaded. It is put into this format. So then you have your timestamp, your date, your device ID, your temperature, wind speed, wind direction, humidity, pressure, and air quality. And that is it for our demo.
Thank you for watching this demonstration on the REWS weather monitoring device. This video was brought to you by the Senior Projects Team 29 at the Department of Computer Science and Engineering.